Hypothesis testing. A hypothesis is a statement about a population's mean or variance. Now, since these parameters are unknown or unobservable, we draw a sample from the population, and based on the results of the sample, we either reject or not reject, in other words, accept the hypothesis. So let's just pause right there and just make sure we understand the big picture. Now, the population represents all possible observations. Now, for some reason, we cannot see what all those values are. So then what we do is we draw a sample from the population, and based on the results of the sample, we can see if the sample either supports or rejects whatever hypothesis we are making about the population. So let's illustrate with an example. Suppose that a fund claims that over the long term, its average return is 1.3% per month. Now, this is a hypothesis because the claim is regarding the population average. So the fund manager is claiming that of all the returns that it has exhibited and will exhibit in the future, the mean is 1.3% per month. Now, to test this claim or hypothesis, the analyst will draw the following sample. So while the analyst does not have access to all the monthly returns of the fund, let's just say that she's able to draw 36 months worth of return data. So that's number of monthly observations over the last 3 years. And based on her sample of 36 observations, she calculates that the average monthly return for the sample is 1.1%. And at the same time, the standard deviation within that sample is 1.4%. Now, here's how it works, ladies and gentlemen. You have 36 observations, but one average, or one mean, I should say. So what would you like to know in addition to these two pieces of data? So if I have 36 observations and one mean, I like to see how dispersed these 36 observations are around the mean. And that's exactly why we have standard deviation. So it's showing you how dispersed these 36 individual observations are around the mean. But ladies and gentlemen, here's where you got to be really careful. We're doing a hypothesis test regarding the mean. So what we want is the dispersion for the mean and not the dispersion for the individual monthly returns. They're two separate things. Are you interested in how dispersed the individual monthly returns are, or are you interested in the dispersion of the sample mean? And this is very important. Since we're doing the test for the mean, I want to know the dispersion for the mean. In other words, I want to know the standard error of the sample mean and not the standard deviation. Two very different things, and you can see why. Because if you're interested in standard error of the sample mean, we take standard deviation and divide it by the square root of the sample size. And the logic there is that the larger the sample size, the less errors there will be in the estimate for the mean. So the first thing I suggest whenever you're doing a hypothesis test for the mean, this is really important, I keep emphasizing, is as soon as you're given the standard deviation data for the sample, convert it to standard error of sample mean. Because if you don't convert it right away, a lot of candidates may end up using the 1.4 for standard error, and of course that would be the incorrect answer. Instead, the standard error of the sample mean is 0.233. And again, this represents dispersion or error around the sample mean estimate, because again, you got to go back to the aerial view. You're drawing a sample, and samples have error. So how much error is there in this estimate for sample mean? 0.233. All right, so let's continue. And there it is. It's a tip. Since we're testing for the mean, we use standard error of the sample mean and not standard deviation. Done. Now the book has 7 steps to hypothesis testing. I have simplified it to just 4 steps. And let's have a look. So the first step is state the null, which is the default hypothesis, and the alternative. So these are mutually exclusive. So for example, what is the claim that's being made about the population mean? The manager is saying that the population average return is 1.3% per month. So that would be your null hypothesis. Therefore, the alternative would be the complement of that. So the alternative would be that the average is not equal to 1.3% per month. Step 2, state the level of significance for this test. Now this will usually be given, and let's just say that the author says that they want a level of significance of 5%. So how do we interpret that 5% level of significance? Here's the logic. Since the sample may contain errors, we are willing to accept the complement of level of significance, which would be 95% of all test results, as a confirmation of the null. Let me go over that again. When the level of significance is 5%, that means we're willing to accept 95% of all test results as a confirmation of the null. Why are you doing this? Well, again, this whole test is based on a sample, and samples have errors. So we need to build a margin of error in our hypothesis test. And how much margin of error are you building in around the null, around this statement? We're willing to give this statement a 95% wide goalpost. Why are you doing this again? To factor in any errors that may be inherent in our sample. So if the test results come in that 5% range, then even after we gave the null a margin of error 95%, we would still reject that because the sample fell outside of the 95% range and ended up in that other 5%. And of course, I'll show you as we progress. So there it is. The margin of error given to the null is 95%. Therefore, only 5% of the test results would lead to rejection of the null. So therefore, the acceptance range for the null is 1 minus the level of significance. And so here it is. So the acceptance range for the null, which is 95%. How did you get that? It's 100 minus the level of significance. Now in step 3, we have to identify the distribution of the test statistic. Now there's 4 distributions. So this is like the playing field for the hypothesis test. There's a Z distribution, T, chi, and F. Now, Z and T is used for tests regarding the mean, whereas chi and F is used for tests regarding variance. When do we use Z? We use Z if the sample is large. On the other hand, we use T distribution if we're looking at a small sample and the population variance is unknown. And with chi and F tests, we'll have a look at it in greater depth once we get to the tests regarding population variance. But for now, we're testing for mean. Now in this example, the test is for the population mean, as I said. And since the population variance is unknown and the sample is small, we're going to use the T distribution. And let's just stop right there, just a couple of seconds. First of all, how do you know if the sample is small or large? That's in real life, that's discretionary. But for practical purposes on the exam, they'll tell you, right? So there isn't some magic cutoff number where sample size is large or small. That lets you know. And the other clue is, the only way we can use T values is if they give us the table or excerpts from the table. So it's a non-issue. Don't worry about whether the sample is small or large. There'll be other clues provided. Now, what is this? What's this T distribution? Well, what are we testing here? We're testing the sample mean. Well, how's the mean distributed? And that's what we're talking about. That's what these guys are right there. So what is the variable, or they call it the test statistic? What are you testing? I'm testing the sample mean. Well, how are these values distributed? And that's where these distinctions come in. And we've identified that it's going to be a T distribution. Now, in the final step, step 4, we do the test. So tip, hypothesis test is a lot like penalty kicks. That's the perfect analogy. So maybe we could stop there and just talk a little bit about how penalty kicks work. No problemo, no problemo. So here's the field, and we'll look at the middle, And what we'll do is we'll put these two goalposts right there. That's it. So this is your net. That is your net, ladies and gentlemen. Now, here's the kicker. If the ball goes in there, you score. So that would be confirmation of the null. But if the ball goes outside the goalposts, then we reject the null. It's that simple. It's that simple. So let's see how we can relate hypothesis tests to penalty kicks. You set up the goalpost first. So in hypothesis testing, we don't call it goalposts. We call it the critical values. And then we see where the ball went. If the ball went inside the goalpost, then that's a confirmation of the null. Now, where the ball went in hypothesis testing, that's referred to as the sample statistic. So that the sample statistic tells you whether the sample came inside the goalpost or outside the goalpost. And if the ball is in between the goalposts, that would mean the sample fell within the null range, then we accept the null. On the other hand, if the ball goes outside the goalpost, it means the sample fell outside the null range, therefore we reject the null, which automatically implies we accept the alternative. Remember, because these two are mutually exclusive, so if you reject this, automatically it implies that you're accepting the alternative. Now, as I illustrated before with the penalty kicks, the goalposts are constructed around the null. So let me just draw that field again because it's so important. So here it is. So if this is our field, this is the middle, and then what you do is you set up the goalposts here and set up the goalpost there. And that's what we're talking about. And so recall that the null statement was that the population average was 1.3. Now the equal implies that the goalpost must be equidistant from the null. In other words, we're willing to accept outcomes on either side of the null. And this is important. This is important when we have to determine whether it's a one-tail or a two-tail test. So how do we distinguish whether it is one-tail or two-tail? You look at the null statement, and if it's an equality, it says here's my hypothesis, and if you're saying it's equal to 1.3, that means I'm willing to accept the values equidistant on either side of the null, so that if the sample falls either here or here, it would be within that margin of error, and then we would accept the null. So therefore, the result is a two-tailed test. And that's the connection right there, ladies and gentlemen. So if you see an equal sign in the hypothesis, it's a two-tailed test. So therefore, the 95% margin of error would be in the middle, right? So this would be the margin error for the null, and this would be the body. So here it is. So do you see how this is like a penalty kick? Here are the goalposts, right? And the null is right in the middle. So this whole test is centered around the null. And I have to sort of go equidistant on either side. Now you could see how the 95% is in the middle because it's a two-tailed test. Therefore, the 5% for the alternative will be split between the two tails. So each tail would get a 2.5% area. So there it is. So you got 2.5% here, 2.5% there, and a 95% margin of error in the middle. And just like the penalty kick analogy, ladies and gentlemen, if the sample falls anywhere here, anywhere within that range, we would say that's attributed to margin of error, and it's falling within null range, so therefore we would accept the null. So even if the sample came all the way here, look how far away it is from the null, we would attribute that to margin of error and say, you know what, after you factor out the margin of error, it's still possible for the null to be true. On the other hand, if the sample comes in here, you say, well, you know what, that is beyond margin of error. So if the sample came here, that's not error, that's a rejection of the null. My sample just simply cannot support the null, and therefore you would accept the alternative. So with that sort of a simplistic overview of how hypothesis test works, the rest is actually not that difficult. We just have to find the goalposts. These are called the critical values, and see where the sample came. So there it is, goalpost, critical values. It's the distance of the goalpost from the null. So this distance right there. And since we're using a t distribution, to get the critical values for t, we need to specify two things. One is degrees of freedom, which is n-1. So in this case, that works out to 35. And then we have to specify the single tail area. So it doesn't matter which tail you're looking at. In both cases, it's 0.025. So now what I'm going to do is I'm going to take you to the t table. We're going to look for these parameters, 35 and 0.025. And see what the t critical value would be. In other words, how far the goalpost would have to be from the null. So here we are. We're looking at the t table, t distribution. And notice that the way to read this table is by specifying the area of one tail. All right. And the two parameters are here, the degrees of freedom and the tail area itself right there. So the degree of freedom continues, it starts from 1 and then continues, picks up from here at 31. But the one we're interested in is degree of freedom of 35 and one tail area of 0.025. So when we triangulate, we get a critical value of 2.03. And that's exactly where we got these values. Now, since the t distribution is symmetrical, the 2.03 would be the goalpost on both the right side and the left sides. But on the left side, of course, it's a negative deviation. So all the table told us is you have to go 2.03 standard errors on either side. So one on this side and one on that side. But if you come on this side, it's just saying you're below. So this is 2.03 standard deviations below the null, whereas this is above the null. But again, since it's a symmetric distribution, the numeric value for the critical value would be the same, 2.03. So ladies and gentlemen, again, if you have that penalty kick analogy in the back of your mind, at this stage the goalposts are set. So what's the next thing? Well, let's see where the ball went in, and that would be your sample statistic, and that's the distance of the sample or the ball from the null. So again, do you see how everything is measured from the null? So first of all, the goalposts are measured from the null, but similarly with the sample, we want to know how far the sample deviated from the null. And that's exactly what a sample or test statistic is. It's right here. Here's the sample. How far did it deviate from the null? But the thing is, we measured in units of standard error. That's it. So we just plug in the values. So here's the sample mean, here's the hypothesized value, and here's the standard error of the mean. So therefore, the sample deviated by negative 0.86 standard errors from the null. So when we go to our table, that's exactly what we see. The sample, so again, starting from the null, the sample only deviated negative 0.86 standard errors. But the goalposts are 2.03 standard errors wide. So therefore, the sample, you could see, fell within null range. So that's like a goal. That means the null wins. So in hypothesis terms, we accept the null. In other words, we don't reject it. And there it is, the decision rule. Since the sample statistic or the ball fell within the critical values, i.e. the goalposts, we accept, i.e. not reject the null at the 5% level of significance. So how do we interpret this in English? So even though the sample mean was 1.1%, and you remember the hypothesis value was 1.3, here's the conclusion. Once we factor in sampling errors, in this case a 95% margin of error, we conclude that it's possible for the hypothesized value, which was 1.3, to be true. In other words, we're saying that the sample being 1.1 And the fact that it's deviating from the hypothesized value can be attributed to sampling error. And therefore, the sample could be seen as supporting the hypothesized value. Now, tip, hypothesis tests and confidence intervals will lead to the same decision. So if we use the same data as the illustration above, and here it is reproduced, so the sample mean is 1.1, the standard error of the sample mean is 0.233, and the critical value, this is if you want like a 95% margin of error, would be 2.03. And again, we showed how we got this from the table. Now, this is also referred to as a reliability factor for a 95% confidence interval. So it's just terminology. Whether we refer to it as critical value or reliability factor, it's the same thing. Basically, it's saying how many standard errors do you need to deviate from the null in order to cover a 95% range. So if we use the confidence interval framework, here it is. We start with a sample mean, and then we have to go on either side in order to construct this range around the estimate for population mean. So we have to go the set number of standard errors, and then we have to specify the value of each standard error. And again, this is all information that we've extracted before. So when we plug in, we get this range for 95% confidence interval around the mu. So in other words, what we're saying here is the following. Now, we don't know what the population average is. However, we are 95% confident that this population average lies somewhere in between those two values. Now, since the null was that the mean is 1.3, you could see that the 1.3 falls within that range. And therefore, the conclusion would be that yes, it's possible for the null statement to be true because it does fall within that specified range.